I want to start it with a simple observation. We see the great success and impact of those large language models, especially following the emergence of the ChatGPTs. So it raises a natural question in our domain. Can we have our own GPT moment in the scientific computing? By the GPT moment, I'm referring to design a machine learning model that can be as general as possible, that can be adapted to different scenarios and different scientific related problems. So today, the story I want to tell is about how this idea could actually be possible and how my work takes concrete steps towards this. To motivate the idea, let me briefly recall what the GPT moment looks like in AI. This moment occurred when models stopped being trained for single narrow tasks, but try to train with massive dataset, try to learn the shared representation across different tasks and modalities. So as you can see on the left, that's the user interface of the ChatGPT. It's a single language model that can help users with writing, reasoning, explaining mathematics, and beyond. And on the right, that's a video produced by Sora. And the Sora is another foundation model uh, that can produce the realistic videos across different scenes and motions. And in fact, similar ideas have begun to emerge in the scientific domains. And so in the next slides, I want to highlight several early successful examples. Um, yeah. So the first example I want to show is a graph cast. It's a wider foundation model that learns the global weather dynamics. And then moving forward to the biology domain, another foundation model I want to show is the AlphaFold. We can use it to predict the protein structures. For both two models, they are trained with massive available dataset, but more importantly, they indicate the possibility of building the foundation models for the scientific domains. Now, when it comes to the scientific computing or computational science, we know many physical problems, they are described by the partial differential equations. So it motivates the central question of today's talk, that it is possible to build a foundation model for the PDE-governed systems. To be more precise, let's outline the goal more precisely. So we want to build a PD foundation model that could generalize across different parameters. For example, different initial and boundary conditions, coefficients, forcing terms, and geometries, or even different PD families. If we can do that, then we may see some immediate impacts in the following regimes. For example, the instant adaptation to new PDEs, new problems, or it could enable the real-time optimizations and controls. But if we take this idea seriously, we want to do that, we may see fundamental challenges in the data generation and preparation. Because for certain applications, as you can see on the right, like turbulence, supernova, or fracture, their simulations are extremely expensive. A single case may take millions or billions CPU hours to run. So at the end of the day, the high-fidelity PD dataset is extremely expensive to generate, and consequently, the scaling the purely data-driven models becomes computationally prohibitive. Okay, but how do we do? What do we do? How do we move forward? Well, we may ask the question in a different way. That is, can we build the PD foundation model without the massive simulation data? So if we go over the successful path of the ChatGPT, we may summarize two ingredients. Number one, a massive training dataset that already exists. Number two, very efficient self-supervised pre-training on the unlabeled data. So when it comes to the scientific computing or computational science, we usually don't have data at scale, but we do have some cheap data. Cheap data, they are called physics, governing equations, or domain knowledge. So it motivates me to propose an alternative path by leveraging the large-scale self-supervised pre-training guided by the governing equations. So at the moment, it's still quite ambitious and very vague. To make this more concrete, let me decompose that into three steps with increasing difficulty and generality. So in the step one, we want to solve such a case. We want to solve a single PDE with neural networks. Here we fix the form of the PDE and the initial and boundary conditions. If this can be done, then we move forward to the second step. Here we want to solve a parametric PDE. In this scenario, we fix the form of the PDE, but we may want to vary certain parameters inside, like the initial or boundary conditions. If this can also be done, then we can go to our final step. In this case, we want to tackle or solve the heterogeneous PDE families. In this case, multiple PDEs are considered simultaneously, and we want to vary any parameters inside. And for all three steps, the only supervision signal I want to use are those governing equations, physics, and domain knowledge. Okay, now let's follow this roadmap to see how we could approach this step by step. In the step one, we want to solve a single PDE with neural networks. And this in fact brings us the framework of physics-informed neural networks, or PINs. So it was proposed in the 2017 and have been recently extensively studied in the recent years. It's basically a machine learning framework that can be used to solve the forward or inverse partial differential equations. The idea of that is quite straightforward. We just consider a very general PDE problem setup. Here we use n to denote a linear or nonlinear differential operator, and we use b to denote the boundary operator. And in this case, we treat the initial condition as a special case of the boundary conditions. And our goal is to train a network to approximate the target PDE solution U, which takes the coordinates as the input and output corresponding solution values. And instead of training this network by fitting the labeled solution data, we try to train this network by imposing underlying physical laws. To be more specific, we formulate such a composite loss. As you can see, this loss function consists of two terms, right? LR of theta and LBC of theta. And for the first term, we call it the PDE residual loss, and we use that to enforce the network to satisfy the PDEs. And for the second term, we call it the boundary condition loss, and we use that to enforce the boundary conditions. And we just train this network by minimizing such a loss function using some gradient descent method. At each iteration, we just evaluate those losses by randomly sample some collocation points in the domain of interest and then minimize the loss. Okay, so after the training process, we hope this loss function can be properly minimized, and we hope those physical constraints can be approximately satisfied. At that moment, we hope our network can approach the underlying PDE solution. And this is the whole idea of pins. To better understand that, let me connect pins with the classical finite element method. So suppose we have such a model problem, the Poisson equation. If we want to solve that with finite element, then first of all, we can approximate the target PDE solution U by a linear combination of some bases, and those bases are the finite element bases. Here I just consider the linear FEM, so they are the hat functions. And for finite element, we want to minimize such objective function. This is basically the PDE residuals in the strong form. At the end of the day, we basically want to determine the coefficient C by solving such a convex quadratic problem. And what's interesting is that those hat functions can be expressed by some ReLU functions. So as a consequence, those two expressions are equivalent to each other, and this implies the linear FEM, the finite element, can be viewed as a special case of the ReLU network with structured weights. And in fact, the pins or deep risk method just generalize this idea by minimizing the PDE residuals in the strong or variational form while allowing those weights trainable. So one main advantage is that we can definitely get greater approximation power due to the flexibility of those bases, but the price we have to pay is the underlying highly non-convex, highly nonlinear optimization problem we need to solve. Okay, and also because of that, pins are notoriously hard to train. I want to illustrate that through a simple example of solving the linear advection equation. Here, C is just a scalar constant. If we want to solve this linear system by pins, then we can formulate such a composite loss. But if we train a vanilla pin model, most likely we may get such a result. As you can see on the right, this is a pin's prediction. It looks reasonable near the initial condition, but quickly collapses to a trivial solution afterward. So what's the reason behind that? If we want to explore the fundamental issue, we may want to check the backpropagated gradients. So in the figure below, I just realized a histogram of the gradients distribution of each individual loss. So the right part, they are the gradients of the PD residual loss, and the blue part, they are the gradients of the initial condition loss. As you can see, the scale of those two distributions are quite different. And basically, the gradients of the PD residual loss are much larger than the ones of the initial condition loss. As a result, the pin's optimization process is biased towards minimizing the PD residuals while ignoring fitting the initial conditions. And this breaks the well-postness of the PD system and causes the model failure. But once we know this is kind of the fundamental issue, actually the solution can be very straightforward. So we can consider such a weighted loss. We still consider the same problem. We consider a weighted loss, and we assign weights to balance the interplay of these two losses and to balance the backpropagated gradients. So we can consider such a formula. By doing that, this can guarantee the weighted gradients will be equal to each other. Okay. And we call this weighting scheme as the just green norm weighting scheme. Now let's see what happens if we apply such a weighting scheme in the pins training. I forgot to mention that this formula can be generalized to the loss function with arbitrary number of terms. And here is the result. So as you can see this time, by applying the weighting scheme, our prediction looks better than before, but still quite far from the reference solution we saw in the earlier slide. So this indicates that there's some other issues in the pins training and we haven't identified and resolved yet. But before I review them, let me introduce a mathematical framework called the neural kernel theory, and you'll see how we apply that to diagnose pins pathologies. So to begin with, I need to introduce that standard formulation of a fit-for neural network. This is defined recursively. We use sigma to denote the activation function. Those W and B are the weights and biases. With this notation, we can define the so-called neural kernel. It's basically an inner product between the network output with not the derivative of the network output with respect to its trainable parameter evaluated at two input points, x and x prime. With that, in fact, we can prove the training dynamics of pins, the training dynamics of the neural networks for the regression task is governed by this ODE system. Well, here we consider the continuous gradient flow. The tau just denote the certain time step of the gradient descent. And the NTK matrix we defined above just serve as a coefficient matrix in this ODE system. And there are two important theorems for this NTK. Under the infinite worth limit means that if we increase the number of hidden neurons to infinity. So the first important theorem is that this NTK matrix at actualization will converge to a deterministic kernel actualization. This kernel doesn't depend on the choice of theta anymore. Secondly, this kernel matrix will remain as a constant matrix during the whole training process under the same infinite worth limit. How is this related to pins? Actually, we can introduce the same theory to pins and analyze its training dynamics. Here we still consider the same model problem, the linear advection equation, by introducing those notations like the boundary operator and the differential operator, and we consider the same loss function. Then we can derive the training dynamics of pins. This time, the coefficient matrix become a block matrix with the detailed definition shown below. And similarly, we can define this coefficient matrix as the NTK of pins, and we use the same notation of k tau. What's interesting is that under the NTK regime, where we assume this matrix doesn't change during the training process, then we use a notation of y tau to denote the error term. Then the training dynamics of pins can be reduced to such a simple ODE system with constant coefficient matrix K0. And if we do the eigen decomposition of the NTK, we can write down the solution of y analytically. This is the final result. So if you observe that, okay, I forgot to explain that. So this y tau is basically a linear combination of the NTK eigenvectors, denoted by Qj, and those coefficients are the e to the minus lambda j tau. The lambda j's are the eigenvalues of the NTK matrix of the pins. There are two important observations or insights. Number one, the eigenvalues of the NTK will quantify the convergence rate of the training error. Higher eigenvalues implies higher convergence rate. Number two, the eigenvectors of the NTK will characterize the features, what kind of features that networks prefer to learn. And down below, I just visualized the eigenvalue distributions of the diagonal NTK matrices, QU and KR. As you can see, the scale of these two distributions is still very different. The eigenvalues of KR is much larger than the ones of KU. This means that the convergence rate of the associated PDE residual loss is much faster than the ones of the initial condition loss. And this is consistent with the unbalanced gradient we see in the earlier slides. Another important observation is that for both two distributions, their eigenvalues decay pretty fast. This means the training process of pins only focus on learning the leading eigenvectors, and those leading eigenvectors correspond to the discretization of some low-frequency functions. And let's actually review another fundamental issue in the PIN's training. That's called the spectral bias. And in fact, spectral bias is very well known already in the machine learning community. It refers to a phenomena that the coordinate-based MLPs prefer to learn simple functions, low-frequency functions in the training, and had a hard time or struggle with learning the high frequencies or find details in the target signal. And in the previous slides, I just reviewed PIN's training also suffer from the same issue. And luckily, the machine learning community already proposed an efficient solution that's called a random feature network. Compared to a standard MLP, this network, it just first projects the coordinates denoted by V into some cosine signals with random sampled frequencies, and we sample this frequency from a Gaussian distribution with variance sigma. Then once we have this embedded feature, we just pass it through a standard fit-for neural networks. What's interesting is that we can improve the eigenvalue distribution of the NTK matrix by tuning this hyperparameter sigma. As you can see on the right, if we increase the sigma from 1 to 10, we get much more flattened eigenvalue distribution. And this indicates that the issue of the spectral bias is mitigated to some extent. Now let's see what happens if we apply this for feature networks in the PIN's training. The results are summarized in the bottom. As you can see, if we combine those two techniques, gray norm and full features, we get much better results, much better predictions than before. But still, there's still some discrepancy between this predicted solution and the reference solution. So this indicates there's still some other issues we haven't identified yet. And another issue I want to discuss is called the violation of the temporal causality. So here I don't want to introduce very rigorous mathematical definition of the temporal causality. I just want to give a very high-level heuristic explanation. So it just means what happens in the future should depend on what happens in the past. But conversely, if what happens in the future could even affect what happens in the past, I just say it violates the temporal causality. To see why pins suffer from that, we have to revisit the definition of the PDE residual loss. So this is the formulation of the PDE residual loss. If you observe that, you may see this formulation treats the temporal and the spatial coordinates equally. And if we further reformulate this PDE residual loss into such a double summation, it's basically we calculate all the PDE residuals and then average over all the spatial collocation points first, and then all the temporal coordinates later. With this double summation, we can define the so-called temporal PDE residual loss, LR of T theta. So it's basically the PD residuals over all the spatial coordinates xj's. With that, if we further discretize this temporal derivative by some numerical schemes, then you can see this defined temporal PD residual loss at time ti will be approximated by such an integral. If you stare at this formula, then you may see the correct minimization of the temporal PD residual loss at time ti requires the correct prediction at ti minus 1. Otherwise, even if this loss goes to 0, it could be meaningless. However, if we go back to the original formulation, all the PD residuals are minimized simultaneously. So the gradients corresponding to the PD residuals at a later time would affect the solution globally, uh, including the predicted solution at earlier time. This is because PINS provides a global approximation of the target PD solution, and any change in the PD parameter in the network parameters will change the predictions globally. And this could even happen before we don't get a good prediction at earlier time. And because of that, PINS training suffer from lots of a poor local minimum and also the error will propagate along the time. So that's the issue of the temporal causality. But once we realize that, the solution could be also straightforward. So we still recall the definition of the temporal PD residual loss, LR of T theta. Then we can consider assigning some temporal weights Wi to each temporal PD residual loss at each Ti. More specifically, we consider such a weighting scheme. By doing that, those weights, those Wi's, will decay exponentially with the accumulated residuals, with the accumulated past residuals. And this could guarantee the temporal PD residual loss at time ti won't decrease, won't be minimized unless prior residuals are small, achieve small values, meaning that they are properly minimized. So this mechanism can encourage the network, the PINS model, to learn the solution progressively, and this is coordinates with how the dynamics evolve along the time, and this mechanism respect the temporal causality. It also can be viewed as a time stepping in the numerical schemes in the continuous sense. Okay, now let's see what happens if we apply this causal weighting scheme in the PINS training. The results are summarized in the bottom. You see, combining all those techniques together, with great norm weighting scheme, random for features, and causal weighting, this time we get pretty good agreement with the reference solution. Okay, so far any questions? If no, I just go ahead and move forward. Well, so actually our story is far from ending yet. If we take a closer look at this particular solution, like what I do in this slide, I further visualize the point-wise arrow in this right panel. If you see the color bar, you see the magnitude is around 0.01. If I further report the relative alpha error is about actually 1%. Honestly, this is not a good result for numerical solvers. Nobody will use a numerical solver that can only achieve such accuracy for such a simple problem. If I use a finite element, I could reach machine precision within a second. So what's wrong here? What prevent pins from reaching machine precision? This is actually related to another fundamental issue in the directional gradient conflicts. So as you can see in this figure, where I summarize two types of the gradient conflicts, the type 1, it refers to gradients in a different magnitude, and we have discussed that in the very early slides. But there is a more subtle gradient conflicts, the type 2, it refers to the directional gradient conflicts. But how to measure that in the PINS training? Well, we propose something called the alignment score to measure the conflicts of n vectors. So it's basically a generalization of the cosine similarity in the sense that when n equals 2, where we only have two vectors, then the defined proposed alignment score is exactly the cosine similarities. Okay, and actually it shares the same meaning. For example, if this score has a value 1, then which means all the n vectors will be perfectly aligned. If this score is equal to 0, then all the n vectors are orthogonal to each other. If this score is -1, then it just means those n vectors are completely opposite. So if we further define some notations, then we can define some more specific metrics that can monitor the bin's training. Here we consider a general composite loss, a summation of LIs. If now we use JK to denote the full gradient at the kth iteration of the gradient descent, and we use JIK to denote the gradient of the ith loss term, Li. Now we can define the so-called intra-step or inter-step gradient alignment scores, where they measure the gradient conflicts of n sublosses of within a certain gradient descent step or cross consecutive steps. So on the top right, I just monitor those scores in the pin's training. Here I use two optimizers, Adam and SOAP. For Adam is a common choice of deep learning and also a standard practice in the pin's implementation. But as you can see for this blue curve, where we use the Adam optimizer, this scores oscillates widely from -1 to 1, indicating that pins suffer from a severe directional gradient conflicts. But however, in contrast, if we replace Adam by SOAP, that is another optimizer I will discuss in the next slides. This time the those alignment scores maintain a value of 1 throughout almost the whole training process. This also indicates that the issue of the directional gradient conflicts are resolved by this optimizer. So what is SOAP and why SOAP is such effective? You'll see that in this slide. So for SOAP, I don't want to go over the full technical details, but I just want to convey the key ideas of SOAP. So SOAP is optimizer proposed by Venus, and it stands for the shampoo with atom in the preconditioner's eigenbasis. For SOAP, actually at each iteration of gradient descent, for the weight matrix WT and the corresponding gradients JT, SOAP just maintain two covariance matrices L and R, and at each iteration, SOAP just apply the atom in the rotated space defined by the eigenvectors of those covariance matrices, where we use this transformation T of X to project the parameters in the original space to the rotated space. Okay, that's the SOAP. And why SOAP is such effective, actually we can connect that to the Newton's method. But before that, let's just prove such a proposition. So basically for a preconditioned gradient descent, the interstep gradient alignment score will satisfy this formula. So this formula just tells you if our preconditioner is closer to the Hessian inverse, then we can get higher alignment scores. In other words, if our preconditioned gradient step is closer to a Newton step, we can get higher alignment scores. I see it. Okay, let me go ahead. Alignment scores. If we further assume that the Gaussian-Newton component provides a good approximation to the true Hessian, then we can write down such an informal theorem. The SOAP will approximate the layer-wise Hessian as a preconditioner. So combining those two results together, that explains why the SOAP can maintain such a high inter-alignment scores. Okay, now let's see what happens if we apply SOAP in the actual model predictions. In the first row, that's our original result where we just achieve error of 1%. But if we apply SOAP on the top of that, you see this time the error can be reduced to 10 to the -6. The improvement is up to fourth order of magnitude. I guess I know what you are thinking about. SOAP just works like a magic. It brings such a huge improvement that this suggests using SOAP is sufficient for the pin's training. Well, that's a good point. So we did an ablation study by removing all those techniques and only apply SOAP. The results are summarized in the bottom. You see this time, if we only apply SOAP, the error increases back to the 70%. So those results really indicates that there's no silver bullet for the pin's training. If we want to reach a reasonable accuracy by pins, we need to resolve all those training pathologies altogether. Otherwise, it could be very difficult. Okay. So far we are using a linear divergent equation for illustration purposes, but all those methods, all those techniques and insights can be applied to a wide range of other PDE systems. But still, this is a simple problem. If we really want to solve more challenging problems, we may want to use networks with larger networks with greater approximation power. However, as you'll see in this slides, the vanilla pins are not scalable. But the scalability is a concept in the machine learning which refers to the accuracy should improve as the network capacities increases. This is a little bit different from the scalability in the computational science. That's more about computational efficiency. But now let's stick with this definition. As you can see on the left, if we use a MLP as a backbone, the error really increases when we increase the number of hidden layers. This indicates that the deeper network of deeper MLP-based pin model yields greater test error. I guess one may argue that this is a well-known issue in the deep learning. Deeper networks are harder to train, and one common solution is by adding the skip connections. That's a fair point. So we employ the ResNet as our backbone and run the same experiment under the analytical hyperparameter setting. You see the results are shown in this green curve. The slope is definitely reduced, but we still get increased error, which means adding the skip connections can't resolve the issue. But in contrast, if we employ this architecture called the PartNet, the results in the blue curve, we can get increased accuracy by increasing number of hidden layers. Okay, next I will discuss why vanilla pins or MLP-based pins suffer from is not scalable, and why PartNet can resolve this issue. So everything starts from an interior error estimate of pin model. So here we only consider elliptic PDE system with the direct boundary conditions, but the similar arguments, similar propositions can be proved, can be extended to the parabolic or hyperbolic ones. It's basically a application of the existing PDE regularity theories. But anyway, let's focus on the elliptic PDEs for illustration purposes. So basically, this estimate tells you the error of U in the H2 norm will be bounded by the pin's loss in the integral form. So from this error estimate, we can get two conclusions. Number one, the training loss of pins will control the convergence of the network output and its derivatives, which means if the training loss goes to zero, then the network output will converge to the PD solution, and the network output derivatives will converge to the solution derivatives as well. And this is up to the order of the PD system. And on the other hand, if the network derivatives has a poor trainability or approximation power, then the training error will not decrease at all. And in fact, in the next slide, you'll see for the network derivative, it will have worse trainability if for deeper pin models. And that's related to how we initialize the neural networks. Okay, now let's first revisit the initialization of MLPs. This is a definition, still defined recursively. We use JL to denote the hidden layers, and we use sigma to denote the activation function. What's important is the initialization scheme. So here I just show the X-virgularis initialization schemes, and there are many other ones. The key those initialization schemes are not randomly chosen, but carefully designed, with the purpose of enabling stable forward and backward propagations. Okay, but however, under the same initialization scheme, we can prove such a proposition. Initialization, the network derivative of a L-layer MLP will satisfy such an inequality, this equality approximately, which means the network derivative will be equal to the product of all the weight matrices across each layer. Clearly, if we use a deeper networks, this expression is more vulnerable to the gradient vanishing or exploding. And if we further assume all the hidden layers have the what D, which means all the hidden layers have a D neurons, then the variance of the network derivative will be bounded by 1 over d. This is actually independent of the network depth, but only related to the network width. So this means that if we want to employ a wider network, then we end up with a more degenerated initialization. So long story in short, the conventional initialization schemes of the MLP will result in the pathological initialization of the network derivatives and of course pins. Okay, how do we resolve that? To address this issue, actually we invented a new architecture called the PDEs. That stands for the physics-informed residual adaptive network. I don't want to go over the full technical details, but I want to just convey the high level ideas. Everything different from the conventional skip connections. This is a conventional one. So we basically add a one identity map that connects the input and outputs, where we use F to denote the nonlinearities. So what we proposed is so-called adaptive skip connection. Compared to the conventional one, we introduce a trainable parameter alpha in the skip connection. And the final output is just a linear interpolation between the input x and the nonlinearity layers. Okay. And there are two important, and we use this alpha as a trainable scalar parameter. There are two important properties. Number one, when alpha is equal to 1, then this residual block will be fully nonlinear. When alpha is equal to 0, then this residual block will be an identity map. What's important is that at transition, we initialize all alphas at 0. So as a result, at transition, the network output will be a linear combination of the coordinates embeddings, let's say the random fruit features. So this essentially gives us a very shallow network initialization, and by doing that, this really avoids the problematic initialization of the deep P models. And due to the trainability of these alphas, these alphas will become non-zero during training, then the approximation power and the network depth will be recovered during the training, and the network will learn the required nonlinearity by itself. So that's the whole idea of the PDEs. Now let's see what happens if we combine all those techniques together and apply them to some more challenging problems. The results are summarized in this table. Here we consider a wide range of PDEs from simple linear wave equation to highly nonlinear curve modular flow at Reynolds number of million or the relative Taylor instabilities. You see, from the second column, that's the conventional pins result. You see, for the most problems, the error is around is almost 100%, indicating that it doesn't work at all. But combining all those the techniques we propose, it could lead to great improvements up to several orders of magnitude. On the right, I want to highlight several animations. For example, the reaction diffusion system, pins can learn the correct pattern formations. Or for the chaotic system, pins can learn the transition from the regular phase to the chaotic phase. Moving forward to the highly nonlinear non-resource equation, like the chromocular flow, pins is able to capture such fine details in this complex spatial temporal dynamics. Or moving forward to the coupled system, like the relative instability, is modeled by the incompressible non-resource equation and coupled with energy equation. You see, pins can still learn such interesting mushroom formations. As another highlight, I want to demonstrate pins potential in the turbulence simulations. Here I consider two canonical benchmarks, the Taylor green vortex and the inhomogeneous flow, the turbulent channel flow. Those animations you see, they are purely done by pins without any numerical measurements, but except for fitting the initial conditions. And what's more important is that pins can also reproduce the key turbulence statistics. For example, the kinetic energy, entropy, also the mean velocity profile, pressure profiles, as well as the Reynolds stresses. Okay, now these are the results of our pins, but if you remember, our goal is to build the PDE foundation models. And this is basically the step one. We use pins to solve a single PDE. Once we have those results, maybe we are more confident to move to the step two. Here we want to solve the parametric PDEs with neural networks. So to see the difference, in fact, for all the previous slides, we are interested in learning a function, which means give a model input vector, and we want it to return another vector. But if we want to solve a parametric PDE, let's say if we have such a standard problem setup, here we use N to denote the linear or nonlinear differential operator, and we use B to denote the boundary operator, and compared to the single PDE system, we use U to denote the input PDE parameter function, and we use S to denote the corresponding PDE solution. Then if we want to solve this system, essentially we are learning the solution operator from the input parameter U to the corresponding solution S over the function spaces. And this in fact goes to the active research area of the operator learning. So the whole rationale between this area is to replace the conventional numerical solvers by some neural surrogates, by some PDE surrogates called the neural operators. Once if this can be done, then after the model training, for new input functions, we can directly get the corresponding PDE solution by evaluating the model for paths. And this could be much faster and simpler, much faster and cheaper than the conventional numerical solvers. And there are two representative frameworks. The first one is DeepONet. The second one is for neural operator. And for the rest of my talk, I'll focus on the DeepONet. So we want to solve a parametric PDE. Actually, we can extend the idea of pins and to do that. And I propose a framework called the physics-informed DeepONet. This is a whole framework. So it can be viewed as a natural extension of pins, but in the operator learning setting, we'll employ the DeepONet as the backbone. Compared to the single PDE solving case, we need additional network called the branch net to process the input parameter U, and we use TruckNet to process the query coordinates Y. The final output just denote the solution at the query coordinate Y, and this is obtained by merging those two subnetworks using an inner product. So I want to illustrate this network through a simple example of learning the antiderivative operator. Here we consider a simple ODE system. If we want to learn the mapping from the forcing term U to the corresponding solution S subject to the zero initial condition, then we just want to learn the antiderivative operator. If we want to learn this operator through a data-driven sense, then we may formulate such a mean square error between the model prediction and the target label data. And then that requires to generate input-output data pairs, and those outputs S, they are from some numerical solvers. But alternatively, we could train this model in a purely physics-informed manner, which means we can formulate such a composite loss function. Similar to pins, we use this LPDE to enforce the ODE system, and we use LSC to enforce the zero initial condition. And in fact, this framework can be generalized to any PDE system as long as you can write down the equations. And on the top right, I just want to visualize the predicted solution and its derivatives for one sample. You see, they are in a good agreement with corresponding numerical solutions pretty well. And in fact, we further test this framework on some standard PDE benchmarks. The results are summarized in this table. We consider different PDEs, and for each PDE, we consider the input functions of different types, like the forcing terms, source terms, or the domain geometries. For all the cases, we can achieve reasonable error below 1%. For the rest of the slide, I just want to highlight several realizations like the advection equation, Econo equation, or Burger's equation. For all the examples, the predicted solutions can achieve a good agreement with their numerical solutions. And it's worth emphasizing again that all trained without any solution measurements. Well, DeepONet is great, but it's not perfect. It basically uses the MLP as the backbone, but however, for high-dimensional inputs, it cannot be that efficient. So to address that issue limitation, we propose a more scalable architecture called the continuous vision transformer. So the high-level idea is to make the vision transformer backbone to be a continuous representation of the target output solution. This is done by conditioning the vision transformer backbone on the query coordinates y through a cross-attention mechanism between the transformer encoder outputs and our coordinates embeddings. One novelty lies in the proposed grid-based embedding, as you can see in this red box. So on the right, there are some details. So we create a uniform grid, Yij, and for each grid point, we create a trainable grid features in the latent space, denoted by F. Then for the grid embedding, it's just an interpolation over all the latent grid features F, where the weights are determined by the distance between the coordinates y and each grid point Yij. Here we use beta, a hyperparameter, to control the locality or sharpness of such an interpolation. So in fact, we can calculate the Lipschitz constant of different embeddings and centralization. As you can see, compared to the standard dense layer or random for features, the proposed embedding, for the proposed embedding, the resulting Lipschitz constant is more controlled by changing this hyperparameter beta. For the first two, their Lipschitz constants are equal in the sense of the expectations. And we further did an ablation study on those embeddings, as you can see on the bottom right. The proposed one gave us the best error convergence during the training. And in fact, we test this architecture on some standard PDE benchmarks in our community and compare it against some state-of-the-art PDE surrogates. You see, this time our model achieves superior accuracy and highlights certain parameter efficiency. On the right, I just want to show some realizations for the benchmarks like the smoked flow or never soaks. Model predictions, you can see our model predictions can capture those fine details in this spatial temporal dynamics across different time steps. Okay, I want to clarify that these models are trained in a purely data-driven uh, manner for the fair comparison, but our goal is to use this backbone for the physics-informed training. So finally, at the end, I want to highlight the physics-informed severity through a case study of modeling the S-melting. So at the end of the day, we want to solve such a Allen-Kane equation where m, L, and lambda, there are some hyperparameters, and our goal is to learn the mapping from the initial condition phi 0 to the spatial temporal global solution phi. Okay, and loss phi 0, we use that to parameterize some ellipses of different major or minor axes. So basically A, B, and theta, they are the hyperparameters. We also rotate this ellipse up to certain angle. On the right there, that's the results. You see for different ellipses, our model can learn the solution pretty accurately. But if we use the DeepONet as backbone, as you can see for the same ellipse, the DeepONet can't even learn or fit the initial condition accurately. To provide more evidence, I just show the error convergence of different models. You see the CVIT yields a better error convergence, and the film layer can further improve the model performance. Okay, now this is pretty much all about my presentation, but at the end, I want to put everything back to the roadmap I presented in the earlier slides, and this is all towards the PDE foundation model. So if you remember, we decompose our goal into 3 steps. In the very first step, we want to solve a single PDE with neural networks. Here, I spend a lot of effort in diagnosing and resolving pins training pathologies, and that leads to the robust pins with improved accuracy. And I also highlight the pin's potential in simulating the turbulence. But still, I have to acknowledge that pins still suffer from the limited accuracy and computational efficiency. And we haven't touched the multiphysics simulations yet. And all these are the open questions we need to investigate in the future. Now we go to the step 2. Here we want to solve a parametric PDEs with neural networks. Here I developed the framework of the PI DeepONet and propose a more scalable architecture called the CVIT. So this is where we are right now. We are still in the early stage of this step. There are more items need to be done. For example, we need to extend this method to more challenging problems as well as the complex geometries. And we also need to fill the gap in the theoretical guarantees in the approximation and the convergence. And I believe this is a great test bed for the PDE constraint optimization problems. And towards the future, I really hope all those techniques could facilitate the emergence of a foundation model for solving heterogeneous PDE families. To this end, we need to develop a unified architecture that could process different kind of physics, and we also need a very efficient physics-informed pre-training. We may borrow the insights or techniques from the first 2 steps, And it's also important to demonstrate the scale and loss with respect to the network capacities as well as the physics. Once we have such a foundation model, it's also necessary to develop the cross-PDE transfer learning techniques so that we can adapt the foundation model to some downstream tasks. And anyway, I really hope those techniques can contribute to the scientific discovery, also the digital twin. Yeah, that's all about my presentation. Thank you for listening.